Here we go. Here is 9.2, regular Markov chains. So in this section, our goal is going to be to basically determine the stationary matrix for a given transition matrix, identify regular Markov chains, solve applications using Markov chains, and then finally using your graphing utility approximation of the stationary matrix. So we kind of already did that. I just showed you that in the last part of 9.1 video, but it's really cool Markov chains. A lot of neat stuff. So basically Markov chains just tell you what the long run behavior is of going from a state to another state as we transition. So returning to that example before, where basically I had you do the 4th year after this drivers, like the low risk and the not low risk, we see basically about 97.488% and 2.512% are in the not low risk category. So, but if you continue to calculate this out into basically a very large number, and if actually you see the 5th or 6th, you're going to see basically a limiting matrix, which is the exact thing that we just showed in the last video. But basically what happens is 97.5% of the drivers will be in the low risk and 2.5% will be in the not low risk. And basically it just becomes stationary there. Like it does not change from that if you continue to increase it to many times over, right? As I have shown with the calculator right here, right? So if you look up here where I have the A and B to the 25th and A and B to the 100th, it's the same. It's called the stationary matrix because basically it just reaches that and then it stops because that is the steady state, if you will. There is another way of finding it instead of just using your calculations with your calculator. You can find it by doing the actual mathematical calculations of the formula of SP equal to S, and this is to determine whether it is a stationary matrix. And so what it means basically is that if you were to multiply this 0.975.025, this basically stationary matrix, by the probability matrix, you should end up getting that same stationary matrix back. In other words, it's like multiplying by the identity, aka multiplying by 1, right? So basically that's what it means. What's really cool about that, and I'll make that a little bit bigger. I mean, it's the same thing that's on the screen, but that's basically what it means. It's like multiplying by 1 because you get back the same stationary matrix. Now, let's suppose you needed to make it a little bit harder and you actually need to figure it out. So, but the long run system will be at the steady state, and that's what I've been calling it, right? This is the steady state that we have here. Later states will change very little, if at all. In this example, the long run number of low risk drivers will be 97.5%, and the number of high risk drivers will be 2.5%. Now, the question of whether or not every Markov chain has a unique stationary matrix can be answered is no. Okay? No. However, if a Markov chain is regular, then it'll have a unique stationary matrix, and successive state matrices will always approach this stationary matrix. So a regular Markov chain, transition matrix P is regular if some power of P has only positive entries. A Markov chain is regular Markov chain if its transition matrix is regular. For example, for the matrix D right here, right, we have D. D squared has only positive entries, so D is regular. So note that the entries in P and all powers of P are always greater than or equal to 0, since they represent probabilities. So positive basically means non-zero, okay? That's a really key note here. As long as they don't say 0, we consider it a regular Markov chain. If it has 0 in it, you're gonna find that there might be an absorbing Markov chain. That's gonna be 9-3, so. Properties of regular Markov chains, basically this is the 3 properties that we'll talk about. There is a unique stationary matrix, SP times equals S. So in other words, the stationary matrix times the probability matrix is going to be equal to the stationary matrix. B, given an initial state matrix S0, the state matrices SK approach the stationary matrix S. In other words, the more you go down the line, the more they should approach that stationary matrix S. Okay? And then if you take your probability transition matrix, P to the K, and raise it to very high power, that'll be your limiting matrix. And I did that actually, like I said, in the last section just because I got excited. But basically, if you took like our P matrix raise it to the 25th, you'll see basically both rows are our stationary matrix. So, but we can also do it a little differently. We can find it by saying S1 and S2, and we can find it the hard way. So I shouldn't say hard way, but the more exciting way. So we can also solve a problem like this, and I'll make this a little bit bigger to walk through what we're going to do. So in this case, we have S1, S2, and then we have our P matrix. So in this case, this is not our P matrix, but a different one. And then that's going to be equal to S1 and S2, right? Because these are the same, right? Just like we had up here. These are the same here. Now, if we go through and multiply it, right? Rows, columns, right? This is a 1 by 2, and this is a 2 by 2, which means the resulting matrix will be a 1 by 2. So we have 0.3 times S1 plus S2, right? Rows, columns as a reminder, right? And that's going to equal S1, right? Because it equals that first part there. And then we'll do rows, columns. So S1 is going to be 0.7. And we're going to have 0 times S2, which means that's just 0, right? But I'm writing in there just so you guys see that, right? This times this row right here. And then it's going to be equal to S2. So those are the two values we have. Now, if you were to try to solve these out, you'll see that these matrices, these are the same equations basically, right? Because this basically says 0.7 S1 is equal to S2, right? If we go over here and subtract 0.3 S1 from both sides, you're going to get 0.7 S1 is equal to S2. Are those the same? Yes, they are. So we need one other thing. There's one other piece of information. S1 plus S2, right? This piece right here, right? If you look at these, if you add both those together, what do they equal? Yeah, that's right, 1. Yep, so they equal 1. And now we have S1 plus S2 equals 1. And that's one other thing that we need. And now basically we can use those two equations to solve the unknowns. And we can put those in a matrix sheet and do reduced row echelon form, or we could find the inverse of the matrix. And we might need to change this just a little bit, right? We need to move that S1 over here. So we have S1 plus S2 equals 1. And we have negative 0.7 S1 plus S2 equals 0. And if you remember, that's like putting it in a matrix like this, 1, 1, 1, negative 0.7, 1, and 0. And then if we do reduced row echelon form, or we call this our A matrix and our B matrix, we can do A inverse times B, right? So you could do one option, RREF, reduced row echelon form, or you can do the A inverse times B is equal to X method as well. So review those. Those are from previous chapters, chapter 4. And so, yeah, we need the other property to find the solution, and that should be the solution that we find for those. So in other words, that means that our stationary matrix, 0.5882, 0.4118, and more than likely, you might have to solve one of these by hand, so you should know that. Now, let's say you just wanted to check whether that's the right answer or not. We can put that matrix in real quick. So second matrix, edit, we'll put it in a C, and we're gonna make that probability matrix a 2 by 2, right? 2 by 2, and we got to put in those numbers of the, where is it? Right here, 0.3, 0.7, 1, and 0. So I got those in, right? Same, awesome. All right. So what I'm going to do is raise that matrix to a very high power. So when I raise it to like the 25th, let's say, does that look close to what our answer is down there? Yeah, like it's 0.5882, and if you notice the curly brackets at the bottom, that means approximately, right? So we're probably gonna have to round just a little bit. I bet if we raise this to the 50th, we're gonna answer that's very similar, right? So looks like that's probably where we're gonna end up. That's another way you can check your answer real quick. All right, and that's exactly what I'm saying here, right? According to theorem 1 of this matrix, the state matrices Sk will approach the stationary matrix S. And the matrices given by successive powers of P, which is what we just did, will approach that limiting matrix, right? That's basically what I did here, right? By doing the higher powers of it over and over again. So pretty cool. You can check it both ways. Now let's do another application example problem here. So a company rates every employee as below average, average, or above average. So right now you're thinking we have 3 states. So I'm gonna make this a little bit bigger. Oops, back up. Right? So right now we know we have a probability matrix. And we know we're gonna have basically, we'll call this above average, average, and below average, right? And in this case, we'll have above average, average, and below average, right? Like if we read this, it says we have below average, average, and above average. Past performance indicates that each year 10% of the below average employees will raise their ratings to average. So below average to average will be 0.1. And below average will, and 25% of the average employees will raise theirs to above average. So average becomes above average at 25%. On the other hand, 15% of average employees will lower their ratings to below average at 15%. And 15% of above average employees will lower their ratings to average. Okay, so we got all those pieces of information that we know. Now we got to read a little bit more of the problem to make sure that we constructed it. Company policies prohibit ratings to change from below average to above average. In other words, you can't jump 2 categories. You can only jump 1 category at all, right? So in other words, that means a below average employee can't jump to above average. And above average can't jump to below average in 1 crack. Okay? Now, that means if we remember that a row must sum to 1, this would be 0.9. In other words, 90% of below average employees will stay below average. Average, if we sum these 2 together, we get 0.4, right? So that means this will be 0.6, and this will be 0.85. And that is our probability transition matrix. So over the long run now, what percentage of employees will see below average ratings, and above average ratings? So we have 2 ways that we can do that, right? We can either do SP is equal to S, or we can just raise P, this probability matrix right here, to a very high power. So let's see. Let's make sure our matrices are correct, our probability transition matrix. Looks like ours are a little inverted, right? This is A minus, A, and A plus. So ours rows, 2 rows should be flipped, right? So it's important to label things and set them up that way. I just wanted to do that as an illustration. If you do it by hand, you can do this calculation, right? Each of these rows times each other, and then you'll need that other formula, or basically equation, to solve that system. So if we go through, that's smaller, we'll have 0.9 S1 plus 0.15 S2 is equal to S1. So we have all those. So we have basically 4 equations, except for 2 of them are linear dependent upon each other. You can use Gauss-Jordan elimination to solve the system, which is the basically reduced row echelon form that I said here, right? And we can obtain that basically our steady state, 0.36, 0.24, and 0.4. So you need to know how to do that by hand, but we can also really quickly check with our calculator as well to raise it to a high power. So I'm going to say, I'm going to rename my matrix. So I put it all in there. I'm going to put it in the way we had it, not necessarily the way that's in there. And I'll just go back and raise C to the 50th power. And what do you notice? We have basically 0.4, 0.24, and 0.359. Well, that's really close to 0.36, 0.24, and 0.4. I just have mine backwards, remember, because we did it A plus, A plus, A, and A minus, whereas they did A minus, A, and A plus. But again, That's one of the beauties now of being able to use technology to solve these. So that's one way that we can check, is basically raising it to a higher and higher power. So note though, if you raise it to too high of a power, your calculator might have an issue and get upset with you. And here are the problems from 9.2. Feel free to ask me any questions you have about chapter 9 and section 2.